Hi everybody, this is Mr. Wright with the temperature and specific heat notes, or temperature and thermodynamic notes. And the first thing we're going to talk about is what temperature really is. It's the fact that it's the average kinetic energy, or the measure of the average kinetic energy in a substance. And so I need you to know how to convert from the different scales of Fahrenheit to Celsius and Celsius to Kelvin and Fahrenheit, or Celsius to Fahrenheit. So let's go over some quick little formulas here real quick and get my pens. So the first formula we're going to use is converting Fahrenheit to Celsius. So I'm going to say that Celsius equals 5 ninths times the temperature in Fahrenheit minus 32. Now here's how I remember this. Celsius is always going to be a lower temperature, so you're going to use the lower fraction of 5 ninths. And since subtracting things makes things lower, you're always going to subtract the 32. And so we're just going to put in the 5 ninths. With the Fahrenheit temperature we're looking for is 98.6 degrees, so I'll put that in here. And then I'm going to subtract 32 from it. Now make sure you do the subtraction first since it's in parentheses. Then multiply it by 5, because 5's on top right here, and then divide it by 9, because 9's on the bottom. And then you end up getting 37 degrees Celsius. Now to get to Kelvin is really, really easy to do. The Kelvin temperature is always the Celsius temperature plus 273, because at 0 degrees Kelvin, all energy and motion stops inside the atom. So you're simply going to take that Celsius temperature you just found, which was 37, add it to 273. So your body temperature, this is not room temperature, this is body temperature here. Your body temperature in Kelvin ends up being 310 K. And they don't say degrees Kelvin. I'm not sure why. They just say 310 K. The next thing we're going to do is convert 22 degrees body temperature. This is not body temperature. This is now room temperature. Sorry about that. And we're going to convert Celsius to Fahrenheit. So on this side, I'm going to have F equals. So since Fahrenheit is always a higher temperature, I'm going to use the higher fraction of 9/5. But this time we're not going to use parentheses. I'm going to say Celsius plus 32. So you're not going to use parentheses at all. The way I remember this, the Celsius sort of looks like a set of parentheses, so you use the parentheses up here, okay? But down here, the Fahrenheit, you forget the parentheses because F stands for forget. So I'm simply going to put in the 9 divided by 5, put in my Celsius temperature of 22 degrees. So you're going to take 9 times 22 divided by 5. Get that answer, then add 32, because Fahrenheit's always a higher number. So we're not subtracting 32, we're adding 32. And this time my room temperature is going to be about 71.6 degrees Fahrenheit. Once again, to get to Kelvin, you simply take the Celsius temperature plus 273. So I'm going to take that 22 degrees Celsius, add 273. So this room right now ends up being about 295 K. This last one is pretty easy, because all you got to do is convert the Celsius to Kelvin. And so we're going to take Kelvin equals Celsius plus 273. So I take 100 degrees Celsius plus 273, and boiling in Kelvin is a blazing 373 K. On number 4, we're going to figure out how much energy would the temperature of a 25-gram graphite rod, that's about the lead in your pencil, increases from 23 degrees Celsius to 84 degrees Celsius. So we're going to heat it up real quick. What's the change in thermal energy? So we're going to be measuring, since we're doing energy, we're going to measure it in joules this time. You can also use calories, which we'll get to in the next problem. So let's use joules first. And they give you the specific heat, which we'll talk about a little bit later, but this is going to be our little c. Little c is going to stand for specific heat. Now the formula we're going to use for this is going to be roughly familiar for you. We're going to use a delta Q. Why? I don't know. I guess some sort of chemist came up with that. I don't know where the Q came from. But the amount of thermal energy always equals Q. So Q is going to be thermal energy. And the formula is pretty easy to remember. I just remember by using MCAT as the medical college admissions test. Okay? So here's what we're going to do. We're going to put in all of these different units now. Now, I want you to notice right here at the 710 joules per kilogram. Since that says kilograms, we got to change these grams up here to kilograms. Well, if you remember, to change that, you divide 25 grams, because there's 1,000 grams in every kilogram. You got to divide it by 1,000. So that ends up being 0.025 kilograms. And I had to look at the specific heat value first right here. Okay? So instead of M, I'm going to put in, instead of 25, rather, I'm going to put in holy cow, what the heck is my calculator now? 0.025 kilograms. Then I'm going to bring down my specific heat, which they gave me right here in the problem. That C is specific heat of 710, and it says joules per kilogram K. It's kilogram degree Kelvin. So these kilograms are now going to cancel out. Now the next thing I got to figure out is the temperature here. Well, the change in temperature is final temperature minus initial temperature. Well, the final temperature is 84. The initial temperature was 23, and that's in K. Well, now my K's are going to cancel out. So that K cancels out with this K. And you end up getting an answer of 1,082.75-ish joules. That doesn't mean anything to you yet, but we'll talk about how many joules are in a fat calorie or a food calorie here in just a little bit. Now let's talk about calories that are in food. Now, if you notice, I want you to think real quickly here, you got to start paying attention to this. See this calorie right here spelled with a capital C? That's a food calorie. And a food calorie is equal to 1,000 little calories. And if you remember from your vocabulary, which you're getting ready to take, a little calorie is the amount of energy needed to raise 1 gram of water. So 1 calorie, that's a little calorie here, is the amount it takes to raise 1 gram of water a whole 1 degree Celsius. So for every 1 degree Celsius it gets hotter, of 1 gram of water, it takes a calorie to do that. Well, I want to know how many food calories, big calories, were burned in food that was used to heat 100 grams of water from 1 degree Celsius to 80 degrees Celsius. Well, if you look at what I just told you here, that is actually the specific heat of water, is 1 calorie, that's a little calorie, per gram degrees Celsius is the specific heat of water. We're going to use that same formula we used in number 4, which is Q equals M cap. So we'll say delta Q, or the amount of heat that we get out of here, thermal energy, is M cap. Let me show you what we got here. I can go ahead and keep the M this time in grams. The reason why I can put 100 grams here is because let's look at the C. See the C right here? It's measured in 1 little calorie per gram degrees Celsius. So now these little grams here are going to cancel out with those little grams here. Now I can also keep my temperature in terms of Celsius as well. So I'm going to take the final temperature, which was 80 degrees Celsius, minus the 25 degrees Celsius. And when you put all this together, you end up getting 5,500 little calories. But that's not what the question asks for. It wants to know how many big calories. Remember we circled this? Well, if there are 1,000 little calories, 1,000 little calories in 1 big calorie, we're going to divide that by 1,000. That gives you 5.5 food calories. So in other words, you have to burn 5.5 food calories in order to get that much energy out of it. Now, I want you to take a look back up at number 4, where it says here, 84 minus 23 Kelvin. You're probably saying, well, that 84 degrees was in Celsius, and that 23 degrees was in Celsius. And I put a K here. Well, if I changed that 84 to Celsius, I would end up getting, if I had 273 to that, I would get 357. And if I added 273 to this 23, I would get 296. Well, if you notice, I'm still going to get the same answer. They both give me an answer of 61. That's 61, and this is 61. So I don't really have to convert Kelvin to Celsius if I'm trying to find the change in temperature. Okay, let's go down to number 6 now. Number 6, it says, what will the final temperature be if I mix 1 liter of 40-degree water with a half a liter of 20-degree water? Well, wouldn't the amount of heat, I'm going to put this little delta Q, that the hot water loses equal the amount of heat that the cold water gains? So I could say that this is going to be negative and this one's going to be positive because the cold's going to gain that much heat. The hot water is going to lose that much heat. Well, if you remember, delta Q, if you look right up here, was the same thing as MCAT. So I could say the amount of heat that this one loses, okay, has to equal the amount of heat that this one gains. And so let's go ahead and put in some math here. 1 liter was 1,000 milliliters. Now, there's one thing you got to know about the density of water is that 1 milliliter of water equals 1 gram. So since we're talking about water here, instead of a mass, instead of putting 1,000 milliliters, I could put in 1,000 grams of water right here. Don't forget that our specific heat is 1. And now I'm going to put in the final temperature of this hot water minus the initial temperature. Well, the initial temperature was 40, so I'm going to go ahead and put in a 40 here. And that's going to equal, well, when you mixed it, this one over here, the mass of this one was only 500. How do I get 500? Well, it's a half a liter or 500 milliliters. And we said that every milliliter is 1 gram, so that means this is 500 grams. And that's times 1. And over here, I'm going to have the final temperature minus 20. The initial temperature was 20. Now, once again, I put these little symbols here wrong. I put a negative here and a positive here. Since we're subtracting right here, that now looks like an equal sign. See where I'm subtracting right there? And I'm subtracting right here. I want to make this side negative because negative times a negative, you look at this times that, that'll give me a positive, and that way the cold water warms up or adds heat. If I'm not going to do that to both sides, it's just that I want to take and multiply this whole thing by a -1. So let's get the math here. If you remember doing the FOIL method, you have to distribute this. So it's going to get a little bit complicated here. Let me see what I can do. I'm going to take 1,000 times the first term, which would be 1,000 TF, minus 1,000 times the second term. That gives you 40,000. This is a little bit difficult math that you haven't used for a while. Equals, now remember this is not going to be a -500, -500 times TF. And then you got distributed to the next one as well, -500 times -20. That gives me a positive 10,000. Hope I did that right. Yeah, positive 10,000. Well, now what we're going to do is we're going to get all the terms on the same side. Let me see if I can't get a little bit more room for me here. All right, so now we've got to take all the terms on the same side here. So I'm going to get all my TFs together. So I'm going to add 500 TF to both sides. So if I add a 500 TF here, that now cancels out. Well, if you do it with one side, you got to do it the other. So now I'm going to have a 500 TF over here. And so I got 1,500 TF equals, now I'm going to get this 40,000 to the other side, so I'm going to add 40,000 on this side. Well, that cancels out to 0. And I'm going to add 40,000 over here. So whatever you do to one side, you got to do the other. So that now adds up to 50,000. We're going to divide both sides by 1,500 to get the TF by itself. And so my final temperature after that cancels out. My final temperature for both of them put together is 33 point something, 33.3 degrees Celsius. So the hardest part of this whole thing was the fact that you make one side, always make the co-side negative, because once again, if you're subtracting these numbers, you got to subtract a negative and make it positive because that cold water's got to heat up. Okay, so I don't know how else to describe that, but just make the cold side, multiply that by negative, and you're in good shape. All right, so let's come back to number 7 here. Now you got a railroad crossing, and if you look on your paper, it's all screwed up here. We're going to look at the bottom number 7 on your worksheet, so it should look like the one you see here. Okay, and I think I fell asleep when I was typing this because I got part of the information up in number 6. It's just horrible. So if you look at number 7, it says, how much will a 10-meter railroad rail expand if it's 10 degrees in the morning and heats up to 37 degrees in the afternoon? And it says its linear coefficient of steel is 11 times 10 to the negative 6. Well, the formula for this, it's actually looks complicated, but it's actually pretty easy. We're going to take delta, that means change in, L, that's how much it's going to change in length. That's what you're looking for. How much will this expand, okay? And then you're going to take the original length of the railroad tie times alpha, which is this linear coefficient, that thing right there. This is going to be a new alpha. Now, you probably thought, well, last chapter, Jesus fish was angular acceleration. Well, goodness knows some chemists had to come along and use our Jesus fish for something else. So anyway, just know that that's going to be a coefficient now. And then we're going to put in delta T. That's the change in temperature. So now all we do is plug in our numbers here. Well, if I want to know how much it's going to change in length, I'm going to put in the original length of 10. So I got 10 meters here. That alpha is 11 times 10 to the negative 6. I'm going to have to give that to you. And the change in temperature was final minus initial, so it's 30. So it's not. Hold on here. It's 37 minus 10. And when you put all this together, you end up getting 0.00132 meters, which is about 1 millimeter, which is about the thickness of your fingernail. Now, you wouldn't think that would be much, but when you put these rails together for miles and miles and miles, all of a sudden it becomes a lot, and the metal can't expand, and you start getting bends in the railroad track, and that's what causes trains to derail. So they have to put these little breaks in the railroad tracks. So if you ever listen to a train go across the railroad tracks and you hear that, what they do, those wheels are going across expansion joints. So when they put the two pieces of metal together, they don't put them right next to each other. They actually have a little gap in here, so that way when it gets hot, those two gaps can expand. You'll also find those on bridges and overpasses before you go over. You'll see these little expansion joints. Okay? Finally, I want you to talk about how much gasoline you'll use if you fill up when it's hot outside, or actually in the morning, and then you go and you top off. This formula here is exactly like the other one, but instead of change in length, we're going to do change in volume. So I'm going to have a change in V. We're going to use the original length. You see how on the volume, you see how the original length and the original volume is the same? The change in L is the same thing as the change in V. Now, instead of using a Jesus fish, they used a beta. So it's a Greek letter beta, and that stands for the coefficient, the volumetric coefficient. So this is a little bit different now. This is a different number. Okay. So they give it to us right here at 950. And then finally, they say the change in temperature is from 1635, so I'm going to have a little change in temperature there. All right, everybody, I found out that I made a few mistakes on here, so I changed my numbers on the problem real quick. I now have 57 liters in a steel tank, just like your worksheet says now. But on your worksheet, I want you to change it. We're going to start off at 16 degrees, and we're going to go up to 35 degrees. On your worksheet, it says it's falling to 16 degrees. Well, I want the temperature to go up, just so you can see how much gas you're going to lose if you fill up in the morning and then your gas tank heats up. So let's look at the change in volume for gasoline first. We're going to look at the gas here, and we're trying to figure out the change in volume of it. Well, The original volume was 57 liters. I'm going to put that in. Now, this beta, or the volumetric expansion for gasoline, I'm going to put in as 9.6 times 10 to the negative fourth. So I'll put that in there. And then it's changing temperature. Once again, the final is going to be 35 now, and the original was 16. So the temperature's rising, it's not falling. And so you will lose 1.04 liters of gasoline. Now you gotta remember the steel tank's also going to expand. So I'm going to put a little steel right here. So we're going to use that same formula. Starts out at 57 liters, same thing as the tank. But the coefficient of volumetric expansion for steel, this is not on your paper, so you might want to write that down, is 35 times 10 to the negative 6. It's a lot less than gas. Times 10 to the negative 6. It's again, same change in temperature. And so the gas tank itself only expands 0.03. Well, if you subtract those two, you're losing 1 liter of gas and it's only 0.03 liters of steel that's expanding. So you still get a 1.01 liters that actually expands out of your gas tank. So you lose a liter of gas. And that's going to cost you almost $1 that you're losing in gasoline just because you filled up in the morning, you drove your car to school, it heated up in the afternoon, it expanded, and it fell out of your gas tank. So actually the best time to fill up is in the evening, and you never want to top off either, because if you top off, you're just going to lose that gas due to expansion. Hope this helps. We'll see you tomorrow. Have a great day. Love you. Bye.